this design practice module 12, we were discussing about concurrent engineering approaches in the last module, and we went through the deliberations of two successive meetings. In one meeting, of course, the teams agreed to design a specification, and then the teams looked at the various process capabilities and the mean machining capabilities of more than one systems of manufacturing processes, in which an output cost was created. In the second meeting again, the quality and the purchasing departments who were still not satisfied with the amount of scrap generated, and also the unit cost, they basically wanted to do further deliberations by changing the tolerance limit to a slightly less tight or less slightly slack tolerance limit, and then in that event, as one could see, the unit output cost changed, it actually reduced because of that. So, we will just proceed ahead with in another concurrent engineering team meeting 3. So, you can understand how this process at the very beginning, at the very outset, tries to balance the aspirations of all the so called team members in a cross functional mode, and how team meeting 3 one can actually in very limited steps be able to arrive at a final form of a design. Okay. So, in this particular team meeting, the cross functional multidisciplinary team compares the results of the two meetings and seeks reduction in the cost of manufacturing. Okay. So, the objective here is further reduction in the cost and also obviously further reduction in the rejects, because they are not happy with the level of rejects that happened over the last deliberation. So, further reduction in number of rejects. And obviously, if the rejects reduce, it is a proper utilization, and you can say that the number of pieces of raw shaft required also get reduced. So, the marketing department comes up with a suggestion here and says that the customer is ready to pay more per unit while keeping these into view, that the number of rejects and the number of raw materials overall reduce, because of which the overall manufacturing cost may be lesser. Okay. And we can probably think of going for the third option, which is the automatic screw cutting machine. This is a much better controlled option. It has a much lower standard deviation. If you may recall, in this particular case, the standard deviation corresponding to an automatic screw cutting machine ASM comes out to be equal to 0.001. Okay. So, the sigma j in this particular case comes out to be 0.001. Mean, of course, is the same shaft dimension which was used in the earlier examples. So, the mean value for this whole manufacturing happens to be about 1 inch diameter. Okay. So, the j in this particular case is corresponding to the third option. Okay. So, that is how we define the mean and the standard deviation for this particular option, and we want to somehow calculate, we want to find out what is going to be the outcome of this particular decision of using the ASM. So, obviously, the unit processing cost of such a machine is very high. The unit processing cost here in this particular case comes out to be equal to $12 okay, per piece. So, other data are pretty much similar as previous meetings, and in this meeting the team wants to know. Go ahead please. So, in this case, although the unit processing cost is more, it may happen that the overall reduction in the rejection may be higher, because of which the number of parts that you have to really machine may be lesser in order to get the required amount of parts for the manufacturing process. Okay. So, in this particular case, let us say in this using the ASM machine, the other data is same. In this meeting, the meeting 3, the team wants to know the unit cost of output, number of units of scrap generated, again the number of raw units required to produce 1000 finished pieces using the ASM system, and you can consider both the tolerances. The slightly tighter tolerances, which are in the range of 1 plus minus 0.003 inches, and then based on the marketing feedback, slightly loose set of tolerances, where this goes to 1 plus minus 0.004 inches. And you can probably check on that in the this is called specification set 1. Okay. So, let us say this is corresponding to k equal to 1, and this is called specification 2. So, corresponding to the j equal to third machine, which is the ASM machine in the particular example problem, you can check what is going to be the efficacy of using this specification and this specification on the third machine in terms of cost. So, number of units scrapped needs to be found out using the third machine on the first specification, okay, YS 31, and as you know, this is equal to KS 31 times of the output unit Y 031, and we can find out the KS again by looking into just the scrap fraction. Okay. So, you know that KS 31 is also the total scrap coefficient 31 divided by 1 minus scrap coefficient 31. Okay. So, in this particular case, we need to determine what is the scrap coefficient, and scrap coefficient can be found out again from the upper and the lower tolerance limits. So, in this case, corresponding to k equal to 1, the tolerance limits happen to be 1.003 inches and 0.997 inches. And so, the phi of z upper tolerance j k, j being 3, k being 1, okay, is equal to 1.003 minus 1.00 divided by the standard deviation 0.001. Okay. So, this corresponds to about 3, and if I looked into so phi of 3, phi of this whole term, and if I looked into the normal distribution tables for corresponding to what would happen if the z equal to 3. So, this corresponds to about 99.8 or 99.9% of the values. Okay. So, it is almost about 0.1%, which is, you can say, the reject, because as you know, the rejects in this case is 1 minus phi z upper j k. I have explained to you in these last presentations about how this happens. This happens to be about close to 0.1%. Okay. So, that is how the upper tolerance unqualified number of pieces are, or percentage of pieces are. Similarly, if I had a lower tolerance unqualified percentage, this corresponds to phi of minus 3, which is same as the 0.1%. In other words, the total number of rejects here is close to about 0.2%. Okay. So, 0.002 divided by 1 minus 0.002, which happens to be again a very small percentage of almost 0.0027. Okay. So, that is how the KS31 is, and so this units number of units scrapped is actually equal to 0.0027 times of 1000, which is about 3. So, only 3 pieces are scrapped if you use the slightly tighter specification on the third machine, automatic screw cutting machine, and the number of raw units. Okay. So, let us find out the number of raw units needed. Number of raw units is again based on yi31, which is equal to ki31 times of y031, that is 1.002 times of 1000. So, you get about 103, you can say 27. Okay. So, it is roughly about 1003 pieces approximately. So, this is what you need to put in the system of the transformation for generating about 1000 OK pieces from the transformation. And if I calculate the unit output cost in the case, so the unit output cost in this particular case, which is x031, happens to be ki31 times of xi31 minus ks31 times of xs31 plus ki31 times the processing cost for the output level yi31. Okay. So, in this particular case, it is 1.0027 times of the cost of the input material, which is about $10 a piece, minus the scrap 0.0027 times of $2, which is the scrap cost, plus the processing cost, which is about $12 times of 1.0027, which is the KI31 value. So, this comes out to be about $22.054. Okay. Similarly, if I wanted to look at the other set of specifications, that is corresponding to k equal to 2, which is 1 plus minus 0.004, slightly loose specifications. So, in this case, it would vary between 1.004, 0.996. So, you can actually find out for this particular tolerance limit, the value of Ks happens to be around almost 0. So, it is almost negligible in having a mean specification for j equal to 3 of 1 and sigma j equal to 3 of 0.002. Okay. So, it is as good as almost having 0.001. I am sorry, this is for the automatic screw machine, this is 0.001. So, it is as good as having almost 0 rejects. Okay. So, in that case, you can make both the purchase and quality departments happy, because you have almost null rejects. Okay. So, in this particular case, the KS32 is 0 and KI32 becomes equal to 1. And so, if I wanted to find out the number of scrapped units, okay. So, number of units scrapped comes out to be KS32 times of Y032, okay, or YO32. So, this is 0. Similarly, number of input units in this case would be KI32 times of Y032, which is actually 1000 pieces. So, exactly 1000 units would be produced from 1000 units sent into the transformation, and the unit cost in this particular case. Okay, so, the unit cost using the ASM case of output, which is x032, happens to be KI32 XI32 minus KS32 XS32 plus KI32 function of YI32, okay, which is 1.00 times of unit cost of the input, $10. So, it is 1.00 times of 10, that is the unit input cost, times of the scrap coefficient, 0 times of almost 0, there is no scrap, sorry, the scrap cost is $2, but there is no scrap. Okay. So, this component is 0, times of 1 times the processing cost, which is again $12 per piece. So, this happens to be about $20, $22 per piece. So, in the third meeting, what was found out is that if the customer is ready to pay a little more and if you are able to use a tighter specification on a automatic screw cutting machine, which is the most precise machine, you can have a tighter specification, so that making the quality people happy, and you can have a relatively very low scrap, which can make the purchase department very happy, because it is not easy to get input shaft materials. Okay, that is the condition of the constraint, and still you can do the job in very close cost to what cost was projected on the other two, that is the engine and the turret lathe system. So, this decision making was actually resulted because of the initial participation of all the different members of the team, okay, of the concurrent engineering approach, in the concurrent engineering approach. So, let us look at a slightly different situation again, when we talk about another concurrent engineering meeting. Okay. So, in this particular meeting, there have been, we have seen dramatic improvements in product quality as well as manufacturing lead time as a result of this cross functional team approach, and scrap has been almost reduced to 0, which address the concerns of the quality. In its earlier deliberations, the team did not consider the influence of the economies of scale of production. So, now we consider that situation and try to find out a sort of a cost, which is cost of machining, which is dependent on the total amount of input to the transformation process. So, a function of yi32, and then try to calculate this in terms of the number of the units, or yi32 in terms of how many number of inputs are needed for the slightly slack specifications or lower expanded specifications of 1 plus minus 0.004 as on the third machine j equal to 3, that is the automatic screw cutting machine. So, let us call it concurrent engineering team meeting number 4, okay. And so, we consider afresh for the tolerance specification one plus minus 0.004 inches, the economies of scale. Let the processing cost depend on the input here as a function relationship $12 minus 0.003 yi32. This equation is based on more sort of objective studying of what is the actual cost, including overheads, labor, etc., to work on an ASM, automatic screw cutting machine, if supposing there is a certain fixed level of input material which goes into the system. So, in this particular case, the processing cost per unit when manufacturing 1000 units is about 9. Okay. So, the processing cost per unit when manufacturing 1000 units is 9, because obviously the economies of scale gets added or gets subtracted from the overall cost in this particular case. Okay. And the unit cost of the output in that event, which is represented in terms of ki32 times of xi32 minus ks32 times of xs32 plus ki32 times of function of fyi32, considering the economies of scale, becomes equal to from the last step, okay, for the slightly slack specifications on the ASM, as 1 cross 10 plus or minus 0 times $2 plus 1 cross 9 becomes equal to $19. So, you are able to consider the economies of scale, the requirement of the quality, the requirement of the purchase, and also being able to produce at the lowest possible cost. Okay. So, the last cost which came on an engine lathe, where these considerations were absent in the second team meeting, was about 19.54 units of currency. So, in this particular case, as you see, that cost has also reduced because of economies of scale, because of this concurrent nature of the approach which is being followed. So, this is the power of, you can say, the concurrent engineering. So, if I wanted to record everything in sort of a matrix form to arrive at a decision making, so we would like to let us say call this the result of interaction between design and manufacturing, and I would call this a sort of a decision table for finally arriving at what is going to be the best process, okay, for process design of these components. So, for the manufacturing technological options, where we have tolerances in inches, okay, of two different kinds. For example, in this kind you have the first set of tolerance, which is 1 plus minus 0.003, and the second set of tolerance, which is 1 plus minus 0.004, which was framed out on the advice of the marketing. And we consider various outputs of the algorithm, like unit cost of the processing of the material, or of the final material which came out from the transformation process, the number of scrap units which got generated, and similarly lead time. You get a decision matrix based on which you could actually conclude about what would be a good process in a certain business environment. Similarly, for the other set of specifications, scrap units, unit cost, and lead time. Okay. So, if all these possibilities are integrated together for the different options which are there. So, you have the turret lathe as j equal to 1 option, the engine lathe corresponding to j equal to 2, and the automatic screw cutting machine corresponding to j equal to 3. So, the unit costs here are 23.97, 21.63, 22.02, and units of currency. Similarly, the scrap generated is 465 in one case, 155 in the other, 3 in the other, and the lead time, again if we calculate using setup times as well as the processing times, 485, 949, and 752. Similarly, for the slightly slack specifications, this cost happens to be 20.37, 19.78, and 22 units of currency. Scrap units happen to be 184 in one case, 46 in another, and 0 in another, and the lead times happen to be 1204, 862, and 750. So, based on the business environment which is there, either it could be a low lead time decision, the lowest lead time being 750 minutes for producing the 1000 pieces, okay, and that too at a reasonable cost, okay, and for 0 units of scrap. And as you know that if I take economies of scale here, so if I add the economies of scale term here, this cost further goes down to about $19. So, at the lowest cost, at the let us say lowest possible lead time, with the highest possible quality, and also making the purchase department happy, you could do an operation in the most costly machine. Okay. So, this can only be possible because of this concurrentness in the approach of how you do the overall designing for the specification. So, in this manner, all the specifications need to be determined for an engineering assembly before getting into the manufacture phase, so that there is a optimal angle to all the manufacturing. So, I think I will close the topic here today, but then in the next topic we will compare between what the economies of scale would rhyme in the serial approach as opposed to this approach, and then we will talk something about product life cycle as well. So, up till then, goodbye. Thank you.